Hello everyone. In this video, we'll be learning how to solve this question. Okay, this is another question on what we call thermal physics. Yeah, we have a student drops two metallic objects into a steel container holding 150 grams of water at 25 degrees Celsius. One object is a 200-gram cube of copper that is initially at 85 degrees Celsius, and the other is a chunk of aluminum that is initially at 5 degrees Celsius. Now, to the surprise of the student, the water reaches a final temperature of 25 degrees Celsius, precisely where it started. What is the mass of aluminum chunk? Now, the student dropped two metallic objects into a container, okay, weighing 120 grams, and the container holds water of mass 150 grams, okay, and the temperature, which is the initial temperature of water, okay, that's the water the container holds, is what? Is 25 degrees Celsius. Now, one object is a 200-gram cube of copper, so which means one of the objects the student dropped into the container holding a 150 gram of water at 25 degrees Celsius is a 200-gram cube of copper, okay, that is initially at 85 degrees Celsius. So which means the copper is at a temperature of 85 degrees Celsius. That means it is hot, okay, before it is dropped into the steel container holding a 150 gram of water at 25 degrees Celsius. Okay, and the other is a chunk of aluminum. Okay, a chunk of aluminum that is initially at 5 degrees Celsius. So which means the second object is a chunk of aluminum dropped into the metallic object, okay, of mass 120 gram, okay, holding 150 grams of water at 25 degrees Celsius. So the initial temperature of the aluminum chunk is 5 degrees Celsius. Okay, so to the surprise of the student, the water reaches a final temperature of 25 degrees Celsius, precisely where it started. That means the temperature, that is after stirring the mixture, the heat lost by the hot object, okay, the heat lost by the hot metallic object, okay, will be equal to the heat gained by the cold substance, okay. That is using what we call conservation of energy, okay. Now, the final temperature of the mixture, which is the maximum steady temperature, that is when thermal equilibrium is reached, okay, that is at thermal equilibrium, the temperature reaches 25 degrees Celsius. Okay, so we have a container, okay, this is a container holding water of mass 150 grams, okay, at 25 degrees Celsius. So let's say this is, so we have an object, now the copper cube. So we have the cube of copper, okay, the cube of copper whose temperature, okay, the temperature of copper is at what? 85 degrees Celsius before it is dropped into the what? Container, the steel container holding water, okay. Then we have a chunk of aluminum. So let's say this is the copper, okay, cube of copper. We have cube of copper, okay. Then we have, this is the what? Chunk of aluminum. Let this represent chunk of aluminum. So we have water, okay. This is water, okay. So, and we know that now, temperature of this is 85 degrees Celsius. Temperature of this, which is the initial temperature, is what? 5 degrees Celsius. So now, when the mixture is now stirred thoroughly to 8 even temperature, okay, now the temperature, okay, the final temperature will be measured, okay, using a thermometer. Okay, that's why I said this is an aspect of calorimetry. When we talk about calorimetry is the science of heat measurement, or is the what? Is the science of heat transferred, okay, associated with physical changes, chemical reactions, or other processes. That is other thermodynamic processes. Thermodynamics. When we say thermodynamics, is a branch of physics, that deals with the study of the relationship between energy, heat, and work. Or it is that branch of physics that deals with the study of the behavior of energy and its interactions with matter at various scales. Okay, so in this case, so we have a system. So this is a system because there's what we call thermodynamic system. A thermodynamic system is a quantity of matter or a region of space that is being studied and analyzed for its thermodynamic properties and behavior. So which means we have a system, and a system can be defined by what we call the boundary. Okay, we have the boundary. The boundary separate the system from the what surrounding. That's the ambience, everything outside. Okay, and this is an open system. We have isolated system, open system, and closed system. But in this case, we have open system. So let's dive into solving the question. Now we have the first thing we have is let's write down the information for water. So we have mass of water. Now mass of water, okay, mass of water is 150 grams. Okay, then initial temperature of water. Initial temperature of water. Initial temperature of water is 25 degrees Celsius. Okay, now we also need the specific heat capacity of water. Now, specific heat capacity of water is that will be 4.18 joules per gram per degree Celsius. So these are the informations for water. Now the next is what? Copper. Now for copper, okay, copper, we know that mass of copper mass of copper is 200 grams. 200 grams. Okay, then the initial temperature is 85 degrees. Initial temperature, okay, is 85 degrees. 85 degree Celsius. So what is now the specific heat capacity of copper? Specific heat capacity of copper would be 0.385. Yeah. So the specific heat capacity of copper is 0.385 joules per gram per degree Celsius. That's for copper. Now, the next is chunk of aluminium. Okay, or we can call it what? Aluminium chunk. Now, in the case of aluminium chunk, remember, we want to calculate mass of aluminium. We want to calculate mass of aluminium, which is, we can call that MAL. Okay, let's designate that with MAL. Okay, what is now the initial temperature of aluminium? Yes, initial temperature of aluminium. That is the aluminium chunk. Okay, the initial temperature is 5 degrees Celsius. 5 degrees Celsius. Yeah. One more thing. Oh yes, we also need the specific heat capacity of aluminium. The specific heat capacity of aluminium, that will be, for aluminium, that will be 0.9. Yeah, 0.9. Specific capacity of aluminium. Wow, so it's not in the question. Okay, that will be 0.99900 joules per gram per degree Celsius. So that's the specific heat capacity of aluminium. Now, because here we are considering CGS systems of units. CGS system of units. So that will be 0.900 joules per gram per degree Celsius. Okay, fine. So now we want to calculate the mass of aluminium chunk. Mass of aluminium chunk. So to be able to calculate the mass of aluminium chunk, now, first thing first, like I said, the system consists of water, copper, and chunk of aluminium. So water absorbs it. That means water gains it. Then aluminium also what? Also gains it. But copper loses it. So which means we need to set up the equation for for what we call conservation of energy. That's heat lost will be equals to heat gain. So using principles of conservation of energy, we know that the total heat loss, the total heat loss, net heat loss, that's heat lost, will be equals to heat gained. Heat loss equals to heat gained. So we know that heat lost by copper. Let's calculate heat loss by copper. Okay, heat loss by copper. So we know that heat loss by copper will be mass of copper multiplied by specific capacity of copper, then multiplied by temperature difference or temperature rise. Okay, so in this case, we're going to have this will be mass of copper. Mass of copper is 200. So we have 200 multiplied by specific capacity of copper, which is 0.85385. Then multiply by, now the first temperature of copper is 85 degrees Celsius. Then the temperature now drops to 25 degrees Celsius. That is when the mixture, when the mixture is stirred thoroughly. When the mixture is stirred thoroughly, then thermal equilibrium is reached. That means during thermal equilibrium or at thermal equilibrium, the temperature reaches 25 degrees Celsius. So which means in this case we have 25 minus 85. So this will be, so heat lost by copper will be 200 multiplied by 0.385 multiplied by negative, that will be 60. Negative 60. So let's get the value for heat loss by copper. That will be 200 multiplied by 0.385, okay, multiplied by 60, and that will be 4620. So we have 4620 joules. Okay, so the heat lost by copper, okay, heat lost by copper, which is this, is 4620 joules. 4620 joules. Okay, yeah, that's it. All right, so now let's now look for the heat gained. Let's talk about heat gained by water and aluminium chunk. So that means water plus aluminium. So we have heat gained by water, okay, that's H2O, plus heat gained by aluminium. Okay, so in this case, now let's talk about the heat gained, okay, by water. So we are using mass of water multiplied by specific capacity of water, then multiply by temperature rise. Now let's look at, now for mass of water we have 150. So this will be 150 multiplied by specific capacity of water, which is 4.18, then multiply by temperature rise. Now remember, the initial temperature of water is what? 25 degrees Celsius. Okay, so to the surprise of the student, okay, to the surprise of the student, the water reaches a final temperature of 25 degrees Celsius, precisely where it started. That means after, when thermal equilibrium, during thermal or at that's thermal equilibrium, okay, the temperature of the water reaches 25 degrees Celsius. That's precisely where it started, okay? And in that case, we're going to have 25 minus 25. So this will be 150 multiplied by 4.18 multiplied by 0. So which means the heat gained by water will be what? 0. Okay. So then for aluminium aluminium, that will be mass of aluminium, then the specific heat capacity of what? Aluminium multiplied by temperature difference. Okay, so we have mass of aluminium is the unknown value multiplied by specific heat capacity of aluminium, that will be 0.9, okay, in CGS, then multiplied by temperature rise. Okay, so the temperature rise, the initial temperature is 5 degrees Celsius. Then, to the surprise of the student, the water reaches a final temperature. So, which means the final temperature is 25, the initial temperature is 5. So, we have mass of aluminium multiplied by 0.9, okay, then multiply by 20. So this would be 18. So we have 18 multiplied by mass of aluminium. So we are going to equate. So we now, by principle of conservation of energy, okay, heat lost equals to heat gained. So heat lost is 4620. Then heat gained is 18 MAL. So when we divide both sides by 18, so we have here that mass of aluminium will be, so what is 4620? Okay, divide by 18. Okay, that will be 256.7 approximately. 256.7. Okay, so which means mass of aluminium, which is MAL, okay, will be approximately 257 grams. 257 grams. Anyways, I got 256.7 grams. Then the approximate, when approximated to now it, to the nearest gram, it will be 257 grams. The noblest pleasure is the joy of understanding. Bye bye.